Okay, yeah, so I will just continue where I left off yesterday. So basically I explained yesterday these non-symmorphic symmetries, and I have derived this equation here, which tells you what the eigenvalues are of this non-symmorphic symmetry operator. So we have seen non-symmorphic symmetries are composed of a point group symmetry, so that is to say a reflection symmetry or a rotation symmetry together with a fractional translation. And if you raise them to some power, you'll get an element of the translation group, and from this property you can derive this equation here, which tells you that within the invariant space of this point group, you can label your Bloch states with the eigenvalues of this non-symmorphic symmetry, and these eigenvalues typically take this form. So basically you have here this exponential factor here, which comes from this shift, and then here there are this other exponential factor here, which basically comes from the spin part of your non-symmorphic operator. So I will now first discuss a very simple model where you can see how these non-symmorphic symmetries, because you have this condition here, lead to band crossings, symmetry-enforced band crossings, and then I will extend these arguments to more complicated cases where we take into account not only a non-symmorphic symmetry, but also a time reversal symmetry or an inversion symmetry, and we'll see that in different cases we get different types of symmetry-enforced band crossings. So basically the first simple model I want to discuss is just in one dimension. So it's a model where we have two atoms in the unit cell. So I can represent this, for example, by triangles like this. So I have one atom which I represent by an up triangle, and another atom which I represent by a down triangle, like this. So then the unit cell contains these two atoms. And I have here, if you wish, a non-symmorphic symmetry. So a screw rotation, twofold screw rotation. Which basically rotates here this triangle along this axis. So this up triangle becomes a down triangle, and then you shift by 1/2 of this lattice translation vector along the invariant space of the rotation axis, which is this axis. And so this type of symmetry is then generically implemented like this on the Hamiltonian. So we have this condition. So the symmetry operator G of k times the Hamiltonian times G inverse has to be equals h of k, where k is restricted here to this invariant rotation axis. And you can basically guess the form of this symmetry operator just by looking at this picture here. So basically we see what the symmetry does. It maps the first atom to the second one because it maps this spin up triangles to the spin down triangles, and then you have a shift to the next unit cell, but only for one of the two atoms, right? So you basically make this rotation, and then you shift by 1/2. So basically this atom stays in the first unit cell, but the second atom moves to the second unit cell. So this is implemented by such a matrix. So it's off diagonal, taking into account this shift from up to this mapping from up triangle to down triangle. And then we have here also a phase factor, which takes into account that one of the two atoms moves to the next unit cell. So e to the minus ik. And of course, if you square this, you must get an element of the translation group. So you can explicitly square now this matrix. And you see, indeed, this gives you unity times just the phase factor, e to the minus ik, which is this translation by one lattice vector. And then, in consistency here with this formula here, we therefore find that we can label the Bloch states by the eigenvalues. So we take the square here from this equation. So we get 2 eigenvalues plus minus, and then the square root of this phase factor. So we have plus minus e to the minus ik half. Right, so we have 2 different Bloch states, one with this eigenvalue plus and one with this eigenvalue minus, and both have this phase factor e to the minus ik half. So then you can basically draw this picture here. You can then think about how must these bands now evolve as I go through the unit cell. So I can have 2 bands because it's a 2 by 2 Hamiltonian. And if I focus first on the momentum k equals 0, basically I can just assume that this Bloch state with eigenvalue plus has higher energy, and the Bloch state with eigenvalue minus has lower energy. And then because this is periodic, I know I must go back to this situation also at the other side of the Brillouin zone at k equals 2 pi. Now I have this momentum-dependent phase factor. So basically at k equals 0, this is just 1. Doesn't change any of the story. But if I go to k equals 2 pi, I get here e to the minus I pi, which gives you an extra factor of minus 1. So basically this one interchanges here these 2 eigenspaces. So that means as you go here from k equals 0 to k equals 2 pi, you must interchange these 2 eigenspaces, and therefore there has to be a band crossing. And so this is the basic mechanism of the symmetry-enforced band crossings due to non-symmorphic symmetries.
Sorry?
Yes?
In your matrix G, if you half translate the translation by half the unit cell, once you have PIK, you know, like the
Yeah, I mean, this is a bit off the convention, right? So here I have basically used this convention that I just label, you know, in real space, I just label the unit cells like this, right? I give both atoms the same real space index. And in that convention, this will take this form. I could take a different convention where I assign different real space indices to these 2 atoms, and then you would get this phase factor e to the minus ik half. And these are basically related via unitary transformations, these 2 conventions. Okay, so this is basically a simple heuristic argument why you must have a band crossing, but you can also prove this with more mathematical rigor. And that's what I'm going to sketch now briefly. And so the argument goes as follows. So basically, this Hamiltonian is a 2 by 2 Hamiltonian. And because it has to be Hermitian, we can in general assume that this can be decomposed as a sum of functions. Yeah, let's call them somehow Qi k times the Pauli matrices. Basically, I could also assume that I have here a constant term, Q0, sigma 0, where these functions Q are just basically periodic functions of the crystal momentum. And so the first insight we have is basically I can neglect this term here because this is just a constant. It's not. I mean, it's just an energy momentum-dependent energy shift, but this will not change the type of band crossings, because this energy shift applies equally to both bands. And the second observation we can make is that this G operator, this non-symmorphic operator, does not commute with sigma 3. So this you can verify explicitly, and therefore this sigma 3 term here is symmetry forbidden because of this condition here. So that means our two-band Hamiltonian basically can be written as just two terms, namely a term which goes like sigma 1 and a term which goes like sigma 3. So that means the Hamiltonian is therefore off diagonal. So we can assume this simple form where we parameterize these off diagonal entries just by Q and Q star, where Q star is complex conjugation. And the diagonal entries are 0. Yeah? Okay, so then we apply this symmetry condition here to this Hamiltonian here. So we have to multiply out these matrices, and basically what you get is this condition. So Q of k e to the ik is equal to Q star k. And we also see here immediately that the spectrum basically of this Hamiltonian is given by the absolute value of this vector Q, and the band crossing occurs therefore at E equals 0, where these two bands, one with plus and one with minus, cross linearly. So we have to show basically that this Q of k is different from 0, and we're going to do this by contradiction. And for that we somehow change to complex variables. So I can introduce this complex phase C equals e to the ik, and I can rewrite this f of k in terms of this variable C. And then basically it's just a rewriting in terms of this variable C. I get then this condition here, just from here, right? So Q of k is now f of C, and this phase e to ik is basically C. And then if I assume that f of C doesn't have any zeros, then I can construct a contradiction, right? So if f of C has no zeros, it means that there is no band crossing. So I can, with this assumption, I can construct a contradiction. So basically, I divide here this equation by f of C, so then get f star C divided by f of C. This I can do only if f of C has no zeros. Is equals to C. And this leads to a contradiction because the C is a phase, and as k goes from 0 to 2 pi, this winds once. So here I have somehow winding once, winding 1. If I let the momentum go through the Brillouin zone, but here on this side, I must have even winding, because I can rewrite this as e to the 2i argument of f of C. So I found a contradiction. So this is inconsistent, right? So the left side has a different winding from the right side. So therefore, this assumption must have been wrong. So f of C actually must have some zeros. And this means there has to be a band crossing. this clear so far? Okay, so then I would move on to more complicated examples. So the first more complicated example that we want to study is a mirror glide symmetry together with yes.
So it's essential that you have this sigma, so this commutation relation with symmetry, right?
Right. Yes, true for this argument, yeah. I mean, you can extend this argument also to multiband systems, but you always need this off-diagonal block to make this work in a simple way. Yeah. Okay, so this first example, basically we will see that this will give rise to whale lines protected by a glide reflection. And so the example space group we're going to use is this number 190, or in the other notation, this is P6 bar 2C. So this space group has a glide reflection, which is of this form. So it lets x, y, and z to minus x, y, and c plus 1/2. And then you also have a spin part, I times sigma x. So we want to consider here the case where spin-orbit coupling is important, where we have to include also the spin part, which ensures that if you square the symmetry, you get this extra -1. So this symmetry basically leaves then in the Brillouin zone two planes invariant, which is shown in this figure. This is are basically kx, ky planes. Kz, ky planes, where kx is either 0 or kx is either pi. And for briefness, I will just focus here on this plane here, which is at the boundary of the Brillouin zone, where kx is equals to pi. And so we can now label the Bloch states in this invariant space by the eigenvalues of the symmetry operator. So using this formula here, where we have to use here this upper entry, which also it's a lower entry actually, which corresponds to the case with spin-orbit coupling. We can take this formula here and evaluate this for the case where P is equal 1 and N is equal 2, right? So it's a twofold symmetry. And we have a translation just by half of a unit vector here along the z-axis, so parallel to the invariant plane. So therefore, this P has to be 1. And you can just read off from this equation there that you find these eigenvalues. So mx of psi, so we have two different eigenvalues, is equals to plus minus I e to the minus I kz half. Okay, and now we want to make this a bit more interesting, so we're going to add another symmetry, and the symmetry we want to add is time reversal symmetry. So this is important, because we want to study non-magnetic systems where time reversal symmetry is always an important symmetry. And we have this spin-orbit coupling, so t squares to -1. And it has this usual form with the spin part, E times sigma y times complex conjugation operator. So what is the role now of this time reversal symmetry? So we have to now first realize that this time inverse symmetry does not leave a general point in the Brillouin zone invariant, because time inverse symmetry maps k to minus k, but it only leaves certain points in the Brillouin zone invariant. And because we focus here on this phase here only, there are basically only 2 points where this symmetry is important. It's namely this M point with the coordinates pi 0, 0. So this is mapped to minus pi 0, 0, and this is of course the same as plus pi 0, 0. And the other point which is left invariant is this L point, which has coordinates pi 0, pi. And again, it's mapped onto itself by time inverse symmetry. So we can use here this symmetry as an additional constraint on the band structure. And in particular, we find from Kramer's theorem that there has to be a degeneracy at these time reversal invariant points, right? So Kramer's theorem says you have twofold degeneracy at these time reversal invariant momenta. So this is a simple algebraic argument you can make to show that you must have two eigenstates which are orthogonal and degenerate if you have a time reversal symmetry which squares to minus 1. So then the question is, what does this now mean if we also have this Clyde reflection symmetry? So in other words, which of these block states here, plus psi plus minus, are paired together at this time reversal invariant momenta? And the answer basically is given by this expression. You see you have here this complex conjugation operator. So this tells you that you must pair here block states whose M Clyde reflection eigenvalue are complex conjugate pairs, right? So you pair up, so you make Kramer's pairs. At these streams. With mx eigenvalues that are complex conjugate pairs. Okay, so basically we can now go ahead and see how we can construct this. So this is shown in this figure B. So I just draw here now a line in this invariant plane kx equals pi from the M point to the L point. So the M point kz is 0, and here kz is pi. So then I have to evaluate here this expression here. So basically at kz equals 0, this is just 1. And I get here eigenvalues plus I and minus I. So the only two possible eigenvalues are plus I and minus I. So how can I form a Kramer's pair here? I have to pair these two different eigenstates. So I have to pair on this side here states with eigenvalue plus I and minus I. That's always the case. For all the bands, you will pair states with eigenvalues plus I and minus I. Now if I go to the other side at the L point, where kz is equals pi, I get here, due to this phase factor, I get e to the I pi half, which is minus I. So, and I multiply this with this I here. So basically get plus or minus 1. Now again, I have this rule here that I have to pair complex conjugate pairs. So what is the complex conjugate of plus 1? It's just also plus 1. And the complex conjugate of minus 1 is minus 1. So here I'll have two different possibilities, right? Either pair minus 1 with itself, or I pair plus 1 with itself. Okay, and now I have to connect somehow the bands along this line such that this pairing is consistent with this rule, and such that the eigenvalue evolves according to this formula here. So I see if I start here kz equals 0 with the plus I state, for example, I see that this has to evolve due to this phase factor here to this state with plus I here, right? So I have this eigenvalue basically winds, and I have to go from here to here. And yeah, similarly for the minus I state, right? The minus I state goes now to -1. And the similar argument here, right? So the plus I state goes to +1, and the minus I state goes to -1. So I can only connect this in such a way with a band crossing. There's no other way how I can connect now these bands along this invariant line. I will always have at least one band crossing. Of course, I could draw something more complicated, right? I mean, this we don't know. It could also be that this band basically goes up and then down, and then I have additional band crossings here. But these band crossings I could remove by bringing down this lower band, but this crossing here is basically non-removable. So this is the essence here of this symmetry-enforced band crossing in this particular case. Because this diagram of these bands looks like hourglass, this has been called hourglass dispersion. And there's one more thing here. So basically I have just considered here one path now connecting M to L. But in principle, I could consider any path within this invariant plane, the kx equals pi plane. So I've considered this path here, but I could also have another path which takes a longer route connecting M to L. And I will find by the same argument again that there has to be some band crossing along this path. So this is true for all the passes. So therefore, this crossing here is not a single point, but actually it forms a line which encloses this endpoint in the Brillouin zone. So I found, due to its non-symmorphic symmetries, I must have, for all the bands, for all the materials within the space group, I must have these veil lines which are protected by this symmetry. Okay, so this is this argument. Is there any questions so far? Okay, so then I would basically give a second, yeah?
Okay, I was distracted, I must admit, but how do you fix the different eigenvalues in the gamma and gamma and M points and so on, and the results? How do you fix that you must have +1, +1, -1?
Yeah, so this is just comes from this time reversal operation, right? If I apply this here, I have this complex conjugation operator, and this tells you that the Kramers pair are formed by states whose mx eigenvalues are complex conjugate pairs. So that's the only information you need, and so therefore, at the endpoint, if you evaluate this factor with kz equals 0, you see that the eigenvalues are always plus I or minus I, and therefore you have this pairing. Okay, but I think it's instructive now to give a second argument which connects to these compatibility relations, which probably you have heard about in the first week from Mois Arroyo and others. And so basically, one can arrive at the same conclusion by looking at these compatibility relations between irreducible representations at these time reversal invariant momenta and at the momentum, general momentum within the glide invariant plane. So I'm just going to repeat some basic facts here about these compatibility relations. Yeah, so basically, I think you have heard this in the first week. So because we want to include spin-orbit coupling, we'll have to consider here the so-called double crystallographic space groups. And they are double-valued irreducible representations. So this is basically because we have this factor -1 to the spin part. We don't consider single groups, but we have to consider the double groups. And so we can label now all the states within this invariant plane in terms of these irreps, of these double-valued irreps of this space group 190, right? So we can use these irreps to label the bands here within this invariant plane, and then look at the compatibility relations between these irreps. And so basically, because we restrict ourselves to certain momenta, what we have is not the full double group, but we have, so at a particular momentum, we just have the little group at this k point. Huh? So at a particular momentum in the Brillouin zone, the full symmetry is reduced to a subgroup. Of the full space group, and this subgroup is called little group. Yeah. So what I use to label these bands is not the irreps of the full group, but the irreps of this little group. And then the third point we need here is these compatibility relations. So I'm going to call these irreps of the little group by the symbol d bar. So bar denotes that this is double valued, d bar of k. So it's a little group at this particular k point. And this little group is, of course, different if I look at the time reversal invariant momentum or a momentum, general momentum in the mirror plane. Okay, so then I can use these compatibility relations to derive or to infer a relation between these irreps at the time reversal invariant momenta and the irreps at the general point in this mirror plane. So this is because there is a group-subgroup relation between these two little groups. So the little group at the trim basically contains or the little group at the general momentum in this invariant plane. And because of this, there is this compatibility relation. So I can subduce representation from this high symmetry point. I can subduce representation also at the low symmetry point. So basically, okay, so this should be probably like this. So I start from this irrep at the trim, and then I can subduce if I now restrict myself to this lower symmetry at the general point in the mirror plane. I can then find a representation in this mirror plane, and I can block diagonalize this, and then I get a irreducible representation. So that's somehow the basic procedure. But okay, this is maybe a bit too abstract, so we can just infer this basically explicitly from this table here. So here I have tabulated here these irreps at for this space group, and at these different high symmetry points. So here, these are the irreps at the M point. This time reversal invariant momentum of this glide mirror and L point. And these are the irreps at a general point within this glide mirror plane. So first of all, I notice that I have here two different kinds of irreps. So here I have two-dimensional irrep, which is a so-called Schnyder irrep, which is already time reversal invariant by itself. And at the L points, I have always one-dimensional irreps, which are complex irreps. So to construct here irreps with time reversal symmetry, I would have to form here also complex conjugate pairs of these. So basically, let's do that. So we're going to look now at the irreps at these two trims. So basically, at the M point, I have just one irrep, this M bar 5, which is already time reversal invariant by itself because it's given by a 2x2 matrix, which is Schnyder. And at the L point, I have to form time reversal invariant irreps by pairing up here complex conjugate pairs. So basically, I have to take here L2 bar with L3 bar and L4 bar with L5 bar. And now I have to think about how do these irreps now split as I go from this time reversal invariant momentum to a general point in the mirror plane. So there the irreps are given by this. So I have to ask myself, as I go away from these Kramers pairs, how do these Kramers pairs split up? So how do these irreps here split up into two irreps of this type? And so basically, this is done by considering a small perturbation just away from this high symmetry point. And then I'll see how I can do the splitting such that these irreps, I get these irreps as in this table. Or in other words, I can basically use also this relation here. I can infer it just by looking at the character of this irrep. So the character is basically just the trace. Because these bands are always continuous, I know that these characters at the high symmetry point has to be equal to the sum of the characters at the low symmetry point. Where I sum here over these two bands into which the Kramers pair splits up. Okay, so yeah, this more or less clear. So maybe you can tell me now how this splitting has to occur. So let's just look at this M point with this M bar 5 irrep. How does this have to split up? Does it split up in two C3 bars or in two C4 bars or in a C3 plus a C4? What do you think? 3 plus 4, exactly, yeah. Yeah, it splits up into 3 plus 4. That's because at the endpoint Kz is equal 0. So you see here, I said here Kz equals 0. I get e to the I pi half, which is basically plus I. And here I get e to the minus I pi half, which is minus I. So this then kind of converts into this plus I minus I here. And I get the same, I get this relation here also satisfied, right? So the character is 0, and the character of these two together will also give 0. And by the similar argument, I'll find that at the L point, so L2 bar, L3 bar, how does this split up? So the L point Kz is equals pi. So how can I split the Kramers pair as I go from the L point to a general point? What do I get? C3, C2, C3 plus what? C3 plus C3, exactly, yeah. And for the other irrep at the L point, I get C4 plus C4. Okay, so now I know how these have to split up, and the bands have to satisfy these compatibility relations. So basically, I can draw a diagram like this. So I have here at the end point the splitting to C3, C4, and at the L point I have these two possibilities. Either I have the irrep L2, L3, which splits into C3, C3, or I have a irrep L4, L5, which splits into C4, C4. So now I have to connect these bands in a continuous way for any path connecting M to L. And the only way I can do this is by a band crossing. So the only way how you can connect the bands such that these compatibility relations are satisfied is by doing this here. And we see again we must have this hourglass type dispersion for any path connecting M to L. So this is actually an hourglass Weyl nodal line. Is there any questions so far? Yes?
The symmetry eigenvalues are related to the particles in some way, right?
Right. Yeah, so you see basically here we have these phase factors here, which, okay, I mean, depends a bit on the convention. You have already erased it, huh? What was the symmetry eigenvalue? Yeah, this should basically, if it's the same convention, it should be identical, yeah. Okay, yeah. So, right, so to summarize, we have found in the space group 190, we have these nodal lines, and these occur for all the bands and for all materials in the space group. So I can now use this strategy to find a new material. So basically, what I'm going to do now next, or what I have done already, is you can look at these databases now. For example, this ICSD from Karlsruhe, and you plug in the space group 190, and then you'll get a list of materials which crystallize in the space group. And from this list, basically, you to make your life easier, you're going to select materials which have just 2 or 3 different atoms. And you will also have to focus on heavy atoms, because here we wanted to have also the effects of spin-orbit coupling. So heavy atoms have strong spin-orbit coupling. And so with these criteria, you get a few examples. And the one we found is this zirconium iridium tin, which is in this space group. And we can then compute the band structure, which is shown here. And indeed, all the bands in this mirror plane, kx equals pi, have this hourglass type dispersion. So they have at least one crossing. So we have always groups of 4 bands which are connected, which form at least one crossing point. There could be other points here which you can remove, basically, but one crossing always remains. And these crossings form a nodal line which encloses the L point in this case, just as the theoretical analysis predicted. And it's nice here also that this happens actually very close to the Fermi energy. So these are Weyl nodal lines which are protected by Berry phase, and so you would expect in this material these drumhead surface states and also other consequences to this Berry phase you have in momentum space. Yeah, okay, so how much time do you have?
If you need
Okay, yeah. Okay, so maybe I just briefly mention then another example. So the second example I've prepared is basically a similar argument as this first example, where we have not a glide mirror symmetry, but we have a 6-fold screw rotation. And you can do the similar analysis either using these symmetry eigenvalues or these compatibility relations, and you'll find that this 6-fold screw rotation give rise to so-called accordion states. Yeah, okay, so this symmetry operator is of this form. So it sends x, y, and z to x minus y, x, z plus 1/6. And then you have also a spin part. Yeah, so this again is, occurs in a hexagonal space group. So here we're going to look at the space group 178. And it's a screw rotation symmetry. So basically in the Brillouin zone, it leaves invariant this line connecting gamma to A. Right, so it rotates along the z-axis by 60 degrees. And there is a shift here by 1/6 along the z-axis. And okay, so I'm not going to repeat this argument in detail, but basically it works very similarly. So you derive first the symmetry eigenvalues, and then you find at these time reversal environmenta gamma and A, you have to form here these complex conjugate pairs of the states. And you find that you have a different pairing of states at the gamma point and at the A point, because you have this phase factor in the symmetry eigenvalues. And then you have to connect now these states in a continuous way as you go from gamma to A. And the only possibility to do this is in such a way here where you have a minimum number of 5 band crossings. And so because this looks a little bit like an accordion, we call this accordion states. And here basically the material is this gold trifluoride. Where this is nicely realized. So you see here the band structure of this material. So here we have this gamma to A line, and we have indeed a group of 12 connected bands which form 5 band crossings, and these band crossings are Weyl points. And they are also exhibit a Chern number, and because of that you have arc surface states. This is shown in this picture here. Yeah, okay, so it's a bit more complicated story. I mean, you also have such protected band crossings along other lines in the Brillouin zone, and where the story is similar. So we have hourglass along this LM line, and accordion states along gamma A, and you know, you just have to repeat the story, and basically you find that there has to be now arc surface states connecting these Weyl points, which is shown here, right? So this is an arc surface state connecting this Weyl point here, the LM line, with the Weyl point at the HK line. Yeah, so maybe I stop here. I would have a third example where I have an off-center symmetry that plays an important role, but I guess you can look this up in the lecture notes. Yeah. Okay.
Actually have one. So up to when you have like only two bands or 2 points, two endpoints, it's clear to me that, I mean, the order doesn't matter because I mean you can shift it. But in the accordion, how do I decide in which order now if I start to invert some of them, I could have different crossings. And how do I decide that, for example, it's 0,5 on top, 0,5, and then 1,4, 1,4, and so on?
Yeah, there's no rule. I mean, so what is drawn here is just the simplest version how you can have a band connectivity. But of course, you could shift these points up and down, and then you would create more crossings.
Okay.
But the point is, you can never remove these 5 crossings here, right? So you must have at least 5 crossings.
I mean, you can have other ones if you start to...
You can have much more complicated. Yeah. Yes.
So do the accordion states also have a topological charge, like a Chern number?
Yeah, okay, so you have these veil points, each of these veil points have a Chern number, but you could also look at, something that characterizes this whole thing here. And yeah, okay, we haven't really done that, but I suppose there is also some invariant, some Wilson loop type invariant, which characterizes the full set of bands. Yeah.
Any other question? So actually, back to the thing you were saying. I mean, you plug the group into the server and you get all the materials that have been cataloged.
Right. Yeah.
But now let's try reverse engineering. So if I tell you the composition of my material, can you predict already which will be the group, or is that too complicated? I mean, one has to realize it in the lab.
Okay, so you just want to give the elements, and then you want to know what is the space group,
crazy,
or what?
Crazy imagining.
Yeah, I mean, there have been some groups who have, tried to predict new materials in this way, right? Where you somehow study the energetics of different arrangements of the atoms. So basically, you have to compute the phonons, and if you have imaginary phonons, it means this arrangement will be unstable. And so there have been some groups had these approaches to, numerically find new materials, but I mean, this has only been successful to some degree, right? I mean, the other problem is once you have predicted the material which should be stable according to theory, you still don't know how you synthesize it, right? You need to have some path also how you can synthesize it. So that's why we focused here only on known materials, because there we are sure that these can be grown and that they are stable.
For the lecture series. We'll move to the coffee break. I guess we can keep it unchanged, so as far